All right, this is 7:30 a.m. Pacific time on December 30th, 2025. My name is Timur. We have Seth with me on the line. Thank you for joining our Mat3ra 2D webinar series. Lately, we've been working on an open source package that is enabling design and the development of two-dimensional materials and interfaces. And today, we'd like to highlight some of its capabilities to you. Let's proceed to the next slide, please. Here you can see some of the capabilities of this package. We can design realistic atomic arrangements that include surfaces, monolayers, interfaces, defects, and atoms, grain boundaries, and many other things that we have to deal with in the real world. And this is our fourth webinar in the series. And today we're going to focus on designing structures that include perturbations. So things like passivation, interesting geometrical shapes, and so on. Let's go to the next slide, please. Now let's briefly go through the rules of engagement for today. The goal of this webinar is to get you comfortable and for you to get to know the functionality. And you don't have to be a platform user, but of course, if you are, you will be able to benefit from this functionality straight away. But all of this is open source, so you'll be able to try it out and deploy this package on your own. We'll share this presentation in a follow-up, and there will be a YouTube video with this recording, so no need to take notes. And if you want to ask questions at any time, please feel free to do so either in chat or in the Q&A session. We'll have a dedicated time at the end to answer all the questions. Now, without further ado, Seth, the floor is yours.
Thank you. Greetings, everybody, and welcome to Mat3ra 2D webinar series. This is part 4, where we're going to use our package for the design of 2D materials to introduce disorder, perturbations, and passivations to the material. First, we're going to take a look at the presentation, which would give you an overview of our approach, and then we'll get to hands-on experience and create some materials. One of the challenges in material science today is that data used to train machine learning models is the data of ideal 3D crystals, while real-world application requires structures that are more complex, such as interfaces, surfaces, or defects. So we need a way to generate such structures. For that, we created the Python package for the rapid design of 2D materials. Our approach has well-defined data structures to help organize information in a database and make it easier to build machine learning models later. We demonstrate the application of our approach with a set of Jupyter notebooks that can be ran in any web browser. And we primarily focus on 2D materials and interfaces because most of the interesting processes occur at the interface, and this is area of increased interest. Here we can see examples, some of the materials that were created using our platform. So grain boundary with a passivation, intercalated interface, and some other forms of interfaces. Let's take a look at the implementation. Our implementation includes 5 components. First is data standards housed in Mat3ra Si. It defines all the entities we work with and how they relate to each other. So this includes materials, common physical properties, and operations that are described in a single consistent way. When we say a slab, interface, or Miller index, it has one clear definition. This allows us to combine simple concepts into more complex ones and track all the changes for provenance. And it's available on GitHub and PyPI. Second is commonly used examples data stored inside of Mat3ra standard data package. It has examples of entities adhering to the data standards. So for example, today we will be using some of the materials from this package. As you can see here, they are listed and their names reflecting the categories of each material, so it's easier to find one. And here we can see the structure of one of the materials. Third one is generic code base, Mat3ra code. which has the implementation of all the entities from the previous first part inside of Python or JavaScript classes, which allows us to operate with them. It's used internally, and we're not going to be reviewing it today. The fourth part is the specific code base, the main made package, Mat3ra made package, which is the Python package for the design of the materials. It has a set of Python tools to create materials, lattice, bases, a set of analyzers to get different properties of the material, and includes builders to create configurations and create different types of materials. And the fifth one is the code usage examples, which is a set of Jupyter notebooks inside of Mat3ra API examples package. These notebooks are self-documented, so users can see how each transformation works, follow a concrete example, and run it immediately. They can be used as a practical tool for day-to-day work to create specific structures, and they naturally support collaboration through sharing, adjustments, and creation of new ones. Last part is to make it available to the end user. We support running those notebooks in a typical environment like Jupyter Lab, but also we have the ability to run these notebooks inside of web browser with the support of PyDiet, Python runtime in a web browser, so you don't need to install anything. And these notebooks can be opened from any web page with the documentation or the tutorial, and without the need to set up anything on your end. You can just run the example and see how to work with some of the functionality. It also allows for transformation with Mat3ra made, as well as the compiled version of Pymagen and AC and any pure Python package. Let's take a look at the implementation details. We split process of material creation into three parts: configuration, transformation, and the result. So, for example, if we want to create an interface, if we want to create a slab, we would start with the bulk material and define properties such as Miller index, thickness, and supercell. This would be our configuration. Next one is a transformation, where we would find a slab builder. And when we apply slab builder to the configuration, as a result, we get material with the metadata of whole transformations and parameters stored for provenance. For example, of more complex materials, we need to divide these steps into define, refine, and build parts. For example, if we have an interface, we need to combine two slabs. So you know the Miller index, you know the thickness, but you might not know the XY supercell for both of the parts, and a strain parameters for the film. So for this, you define slab configuration for both film and substrate, as you did before. Then you use interface analyzer, where you fit these two configurations, and it gives you the resulting interfaces, multiple interfaces that are coherent within the given max area. For example, if you use interface strain analyzer with Zur and McGill ZSL, Zur and McGill superlattice algorithm, as a result, you get an interface, multiple interface configurations, and you can sort those by strain or size depending on what you need. And then you use interface builder to build selected interface, and as a result, get the material with all the metadata about the transformations and how it was created, stored. To make it easier to find specific material or transformation, we use such categorization, where we split materials first by domain of pristine structures, such as ideal crystal, compound pristine structures, such as interface between two slabs, defective structures, such as adatom or interstitial defect, and process structures, such as perturbation or passivation. After domain, we have dimensionalities from 3D to 0D. And the last, each of them has the category. Some categories have variants depending on how the structure was achieved. For example, for interface, you can have a simple interface without no strain matching, or the one that was created using ZSL algorithm. Today, we'll be focusing on process structures of all of the dimensionalities, so perturbation and two types of passivations. So now we're coming to hands-on demonstration. And today we're going to be reviewing the Materials Designer app, and we're going to be using some of the materials from Standata. Within it, we're going to be using Jupyter Light Transformation inside of Materials Designer to create a set of materials. We'll introduce disorder to silicon oxide, hafnium oxide, and we'll create a heterostructure, an interface between them. Then we're going to add a perturbation of some ripple wave inside of graphene. Then we're going to create passivated nanoribbon, and then two silicon structures, two different silicon structures passivated with hydrogen. We were asked repeatedly to add functionality, to add some sort of disorder to the material, and one of the ways to introduce disorder into material is to shift atoms from their equilibrium according to a thermal distribution. This mimics thermal motion while preserving the overall structure. So this is our first example, where we have silicon and hafnia, silicon oxide and hafnia bulk structures. We want to introduce disorder and create an interface. So this is the steps we need to take. So first we will import structures from Standata within the Materials Designer page. So we import output, Standata. We're going to see this in the hands-on. Again, code is just to make, code is just to remind what we're going to be viewing later. So no need to read it well right now or write it down. We're going to see the example in a minute. To introduce disorder, we need to create Maxwell displacement function from the Mat3ra made tools. We'll pass material, we'll pass disorder parameter, which here is a parameter which is temperature-like around EV, the same order as electron volts. Then we have the random seed, which lets you reliably repeat the same perturbation applied to the same material. If you change different random seeds, you get different repeatable changes. If you need to have completely random structure each time, you can set random seed to none. Then we have a flag whether the mass is used. So whether we using mass of each element to get the displacement for mass dependent. So we apply this function to each of the bulk materials, and we get disorder, and we introduce disorder. Then we're going to create slabs, and we discussed the slab creation in one of the previous webinars. So we're just going to state that we use create slab function, create two slabs, and then we create an interface between the slabs. And as a result, we should get the structure. So now we'll go to materialsdesigner.mat3ra.com to create this structure. we'll go to input output to import two materials. Import from standard data. Search for silicon oxide. CO2. Okay, because it's called okay. Silicon oxide in quartz form, and then hafnium oxide. We'll take this one for the example. We can remove silicon. So then we want to introduce the disorder. We go to advanced Jupyter light transformation. Here at the top, we select the material that we want to perform operations on, for example, silicon oxide this time. And here, excuse me, here we have the notebook that shows all of the notebooks that are available, and they're structured according to the categorization. So we'll scroll all the way down to the fifth part, which is perturbations, and get the perturbation thermal disorder. Open the notebook. Here, notebook explains how to operate with it. We want to set material index should be 0. That's what we operate with, and we set the sort of parameter to be around 3 electron volts. Its effective temperature. Let's have a random seed, and we don't want to create supercell. If we run, the packages should be installed quickly. We'll get the material, preview it here. And then we're going to introduce the disorder using the function coming from the package. So here's the preview of the material. If we submit, we should see that some disorder was introduced. And if we toggle bonds, we see that atoms shifted their position. Now we need to apply the same thing for hafnium oxide. And go the same advanced Jupyter light transformation, select hafnium oxide, scroll to the notebook. We can add, for this material, we can add a larger disorder, for example, at 4 electron volts. And if we run all cells, we should have the same procedure. Since I closed the whole Jupyter light transformation window, we need to reinstall the packages into the notebook. But if we keep it open, which we're going to see next time, you don't need to reinstall again. Okay, again, we added a disorder. And here we can see that in crystal basis viewer, we see that some of the atoms are shown to be too close. And this is expected because we introduced random disorder, and they rely on the atomic radii to detect this. So now we're going to go and create the interface. This we can do with using another option to open Jupyter Light, which is View, Jupyter Light Session, and it should open Drawer from the bottom, which you can scroll up and down, and this will allow you to change, preserve any action inside of the notebook. So here we're going to go to multi-material structures, interface with Zurn-McGill strain matching. And here we just need to select the materials that we want to create the structure from. So for film, we're going to do hafnium oxide. So from the sidebar materials, so it has the third index. Then we need to set the silicon substrate to be silicon and to have one-on-one orientation, we probably might increase the thickness to see more of the material. And we can say set any interface distance, vacuum, and other parameters for the ZSL algorithm. Again, this was all covered in one of the previous webinars, the first one, I believe. So we'll just using the structures today, using the previous functionality today. So we should preview materials and as a result we create slab configurations. Here's the analyzer, and we should see the map of the strain versus size shortly, from which we'll by default select the one with the lowest strain. We don't really care about strain here because we did introduce disorder and it still needs some relaxation, but we should preview the material. Okay, maybe because we had a lot of bonds. So as a result, we can see these structures appeared. Let me just maybe close the window. Okay. So this is the final structure that we achieved. If we go to the next example, here we're going to be working with addition of perturbations. And we're going to create a ripple inside of Graphene according to some function. So we want to start with the Graphene monolayer, create a supercell, and introduce deformation. First, we're going to be using Mat3ra data, importing Graphene, creating a supercell with the function, and then we will apply the perturbation. This we use by using the create perturbation function, where you can specify any varied function within the SymPy syntax, which is basically just writing typical Python functions. For example, we have sinus and different other functions. Then we're going to pass material to the supercell, use the perturbation function we defined at the top, and then we have a flag whether to have it isometric or not. So whether to preserve the, if we set it to be true, we're going to preserve the geodesic distance between atoms along the function surface. If we're building for 2D material, so it's going to shrink or extend the supercell, to extend the unit cell to preserve the distances, and whether to use Cartesian coordinates or not. Since here we're using X and Y to be as a crystal, we set it to false. Then after we apply the function, we should get the structure. So again, we're going to be importing from some data. Graphene is the first one. So we can go to advanced Jupyter-like transformation. Graphene is selected as a material and scroll down to perturbations. Again, the on the bottom. And here we can go have two types of perturbation. One was the example of sine wave, and here is any custom function that you can specify with the SumPy. So whether to preserve geodesic distance, supercell matrix, and then the function here we specify it in a editable format. So this is the same sine along x and y, but we can change the amplitude or wavelength or phase. So if we run maybe let's make it supercell of smaller size. It's faster. If we run the cells, we should again install the packages, preview the imported material. So when you describe the function, you're going to need to provide the variable names, if it's XYZ, for SumPy to work, and then create any function that you can modify. So we can write any valid function and then see, and then apply it to the material. Probably need to close the Jupyter Light so it doesn't interfere. Let me restart. Sometimes if you have two windows of Jupyter Light session open, the web nature of this might interfere with web worker. So it might be good to have just one Jupyter Light open in one browser. So we should wait to preview material. We can see PyDiet is being busy. Yeah, maybe the structure is too large for the review here, but we see it sent to the output materials. And we should be able to preview it. Okay, for the next example, we're going to be using passivation, and we're going to passivate the surface. So here we want to take a structure of reconstructed silicon surface 001 and passivate it according to the example in this study. We're going to import, we have silicon 001 or 100 reconstructed inside of the Mat3ra data, for examples. And in this notebook, we're going to be doing the adjustment to make the reconstructed structure that we got from the source to match the one that is presented in the publication. So we'll need to find the coordinates and change and adjust one. So it's all done in the notebook. So we just need to move this atom, which is second to highest, up to the same level as this one to match the structure. We're going to see this in the notebook. Next, we're going to be passivating the surface, and here we're using the function to passivate surface. We specify passivant as the element, the bond length, which is the same bond length from which atom has been passivated, and then the surface, whether it's top, bottom, or both. Shadowing radius in angstroms, and depth to search for the surface. So what is the shadowing radius? Each atom, when we look from any of the direction of top or bottom along Z, we can see an atom, and the shadowing radius is some radius that blocks the next atom to be perceived as a surface one. So here we can see that this atom has some shadowing radius and blocks this one, so this is not a surface. This blocks this one, so it's not a surface. But this atom is not covered, so not shadowed by anything, so it can be passivated. And the depth is to how deep into the structure below the surface you want to see the surface. So you can leave out some of the structures by making depth smaller and thus making it faster to run. Then we use passivate surface, passing a slab and all the properties, and we should get the passivated structure. For this example, we're going to be using the example provided by example from specific examples. So on this main file folder that was open, we can go to specific examples and passivation, find passivation of surface. This is the notebook that reproduces material from the publication. So here we have all of the properties selected, such as material we want to get, shading radius, etc. And we can run the notebook to get the materials, install the packages, and then create a passivation. Here we're going to see shortly the adjustments that were being necessary for the structure. So this is just basically taking all the coordinates of the silicon that we're going to see here, searching for sort them by Z coordinate, get the highest one, adjust it accordingly, and then we can passivate the surface with the function, and as a result get the material. If we toggle bonds on, so if we increase the atomic radii to be large and maybe prolong the structure, repeat the structure, we can see that this is how it looks if it's surface. So all the surface is covered. And for day-to-day use of this structure of this notebook, we can scroll down to we can go to the introduction notebooks and go to the passivation, surface passivation, and use this notebook that explains how to use it to passivate any other slab. So we can create a slab from the sidebar materials and passivate it here. Next example is going to be passivation of nanoribbon, where we need to create a nanoribbon and then add passivation and then passivate the dangling bonds. So we'll import the material, graphene in this case again, create a nanoribbon, and this was covered in the previous webinar. And then after we get the nanoribbon, we can analyze it with the radial distribution function. So we'll pass the nanoribbon and cutoff parameter and see how many atoms, what's the density of atoms around at each distance from the atom, so that we can select the cutoff distance for the neighbor's search. Here is going to should be larger than this value, so we can set it to 2, for example, or larger. So we need to get existing coordination. So to passivate dangling bonds, we need to find other coordinated atoms. So if atom is inside of the bulk of the structure or closer to the center for nanoribbon, then each atom has set of neighbors. Usually it's the same. For example, for graphene, it's in this orientation or in the opposite orientation, and you have three or more neighbors. So within the cutoff distance that we selected, we just have 3 neighbors. If we have atom that's on the side and it has only 2 neighbors, so that means that one of the bond is missing, and this is what we're going to be passivating. So we get the unique coordination numbers to get a feel for the new material. For the new material, we can get understanding how many coordination is there, and we can see the distribution of coordinations so that you can select the threshold correctly. And then we're using the passivate dangling bonds functionality, where we pass the same passive unhand bond length as previously. Shadowing radius, in this case, it's the neighbor search radius. And then the coordination threshold. If less or equal number of neighbors, we passivate this material. We mark this atom to be under-coordinated, and then we can choose how many of bonds to passivate. We can passivate 0, 1, or 2, or more, depending on up to the one that's missing. So, and as a result, we should get the nanoribbon passivated. Okay, we can open this structure when we have graphene. And if we, again, go to advanced Jupyter transformation, we should be able to, okay, we have selected graphene, create a nanoribbon. Just with the default parameters. So that we can passivate it. Again, we need to close the Jupyter Lite in the other tab so that it didn't slow down this one. So here we're just creating a nanoribbon that we're going to be using in the next step. Okay, no input materials found. This means that when we reloaded the Jupyter notebook, we didn't register the materials input. So we can just probably select and deselect, and it should see, and if we run all, it should see the materials. Yes, retrieve materials. Okay, we get the nanoribbon. Then we're going to take this and passivate. So we go to advanced Jupyter transformation. We're going to select the material to be this nanoribbon and scroll down to passivation, edge passivation. So edge passivation is as opposed to surface passivation, where we do calculate the under coordinations. So this is the same thing, edge or under coordination based passivation. We can just hit run. So this is the same settings: coordination threshold, coordination search radius, and number of bonds to passivate. But I'm going to show you, in case we have a different material, how to adjust the values if we see some different profile on the RDF plot. Here's the structure preview. We can see the plot, the same as was in the presentation. And we want to get we see the unique coordination numbers, 2 and 3, and the selection of the threshold. So it explains what's going to be happening. Atoms will be passivated. Then we pass the properties of passivation parameters to the function, and we get the result, the structure, passivated structure. And the orientation of bonds is searched from the bulk of the material. So we have two different orientations for each atom, this direction, or let's say in this direction. So, and the algorithm matches the missing bonds based on those that are present inside of the material. So that's why we get this orientation. Okay, let's try to create to set the coordination selection interactive. Let's set this to true. And let's say we want to increase the coordination search radius. So here we present it with the plot, and we can provide the threshold value from here. So it's going to be the same because it's the same material. So the result is the same. Passivated structure. So next one is going to be two different silicon structures. One is the silicon nanowire. So again, here we take the publication and we reproduce the material from there. We did this in one of the previous webinars where we built the silicon structure. So here we're building on top of this to passivate that structure. So we would import material, silicon, create a slab in the specific orientation, and then we need to rotate and cut the nanowire. This was discussed in one of the previous webinars. So after we get the material, we need to passivate dangling bonds. And so we specify all the parameters. And then here we set coordination threshold to be 3, because typical is 4 and all that has less than 4 are under-coordinated. And we want to passivate two bonds. At maximum 2 bonds. So if it's just 1 missing, we passivate 1. If it's 2 missing, we passivate 2. If we're missing 3, we just passivate 2. So, and as a result, we should get the structure. Okay, we have all closed. Here we can go to advanced Jupyter information. And again, since it was example from the publication, we can find this inside of the specific examples and passivation of edge nanowires silicon notebook. We here have the preview that shows what we expect. And then all the settings that we've seen just now. We can run the cell, although it already did the run from the previous test. So we're waiting for installation. And we should see the structure for the supercell and later the nanowire appear here and be visualized. So here's the structure of nanowire. Then we can see the RDF plot. with the distribution of atoms around each of them, and we want to set the threshold to be 2.5, so something larger than this value. We see all the unique coordination numbers of 2, 3, and 4, and we decide that everything that's 3 or 2 is under-coordinated. Then we pass the properties to the passivate dangling bonds function, and as a result, when we apply it, we should get the structure. Yes. And also we can see that there's no atoms at the top, no hydrogen atoms, because we respect the periodic boundary conditions when getting the coordination, so that we can repeat the structure and get the correct structure. And okay, I think it was all of the examples. We have a set of notebooks for different use cases at jupyterlightmatter.com, so where you can see examples here if we open the interaction notebook. Also, all of this available via materialsdesigner.com, where we can work with the materials separately, or if we open the platform, then we should be able to create materials. So the platform new Mat3ra.com, you can open the materials, create material, and we see the materials design on the side of it, where we can also get the Jupyter Light transformation and start building structures. It should run. So today we showed the Mat3ra made package for the design of 3D materials. We showed how to use it with examples from Mat3ra API examples, and created some real-world materials. This is all available in jupyterlightmatter.com, as well from Materials Designer and from the web app. All the code is open source, and we welcome contributions. So I think now we can get to the questions.
All right. Thank you, Seth, for the presentation. Let's see if we have any questions from the audience first. You're welcome to raise a hand or put your questions in the chat or the Q&A session. I don't think I see anything just yet, so maybe we can start with demonstrating how to input some of the materials when people can't find them in the STEM data. What if you need to start with a material that is not available from there?
Yes, so STEM data doesn't have all of the materials. We have a list of some handful most commonly used ones, but you can, if you're in a standalone designer mode, you can upload materials from disk, for example. So here we can upload files. Interesting. Well, we can upload them by dragging and dropping. For if we have some of the materials with the format. Okay, for example, we can go to, if you have CIF files or Postgre, we can go to the specific notebooks, special notebooks that allows you to import any material. So if we scroll down to the other import data, you can get materials with any format that is supported by ASC. And here you need to be opening the uploads folder, where you can, where all of the materials are saved. And for example, here we have the CIF file. We can get some other CIF file. If we can search for, if you have some. You just need to find some example of CIF file. If we have it on the, but if you store some of the materials here, for example, here we have CIF file. If we run this notebook, we should get the, and we do not enforce formats, it should read all of the materials that are here and get us the structure.
All right, I think we have demonstrated how to do that previously, so please find the import notebook in the list at the top and use that to import files in many different formats. We support both crystal structures and CIF and POSCAR and XYZ and quantum espresso, and even things like mol for molecular configurations. Now, maybe we can talk a little bit about how to use this functionality outside of JupyterLite. If someone would like to use it locally on inside their IDE or in a Python session.
Yes, so we have so if we open the API examples, we can get the API examples from GitHub, and we can open it in any IDE, for example, VS Code or Jupyter Lab. So, and here we can have notebooks. For example, this one or any of those that we reviewed today. So it's under the other materials designer category. Here for structures, so the passivation of edge here. And we have some materials in upload folder, which is by default it's nickel and graphene. And I think this one's from one of my previous runs. And if we have the Python selected, we should run. Okay, let me.
Anyway, with a little bit of tweaking, I think you should be able to utilize the local installation.
Wrong material. It was some issue with the material that I saved before. Yeah. So the passivation. Okay, for passivation, you need to select actually the slab structure.
All right, the convention is that we have designed these notebooks to be able to run both on the web. That's what we've been demonstrating throughout the webinar. And locally, if you have a Jupyter session or any kind of development environment where you can run the same notebook on your local system. It might require some installation, but we try to make it as easy as possible. And then if you have any questions about how to utilize this functionality, if something doesn't work or it's something is not straightforward, then please contact us using the support channels. If you go to Mat3ra platform at mat3ra.com or platform-new, the new iteration of the platform, there is a support channel available in the side, the left sidebar, and we'll be able to assist you with getting set up with this. All right, should we briefly speak about the upcoming functionality for the next few months?
Yes, we are planning to add the ability to create workflows and run jobs from within the Jupyter session. So after we created the material, we should be able to create a workflow and run the calculation. So here, for example, we have just one prototyping structure where we have band gap as example. So you'll be able to select a material from the folder that you created before, find the workflow, switch relaxations, set up model, and adjust some of the parameters for the workflow for the units, and then run this and be able to log in with the platform and execute the job.
I think we might be previewing too much, so that let's not show too much so that people still have a reason to join future webinars. But the idea is that now we've been focusing mostly on setting the initial stage of a simulation where we create a material structure. It has to still be realistic. It has to have defects, disorder, and many other aspects. And our next step is going to be to simulate the structure to understand its properties. So that's what we're going to be focusing throughout 2026. And then the two webinars of the next year will demonstrate how to reproduce specific examples from specific publications that introduce additional complexity in designing the structures. All right. If there are no other questions, I think at this point we'll conclude our 2025 sessions. Thank you, Seth. Thank you, everybody who joined us today. We'll meet again next month. Bye.
Thank you.